Welcome to this episode of Mentors at Your Benchside, the podcast giving you advice, tips and tools for getting the most out of your research. I'm Adam Pawson, and today I'll be talking to you about some of the most common issues that can easily be overlooked during centrifugation and why they are so important for proper handling of a centrifuge. We've all heard about centrifugation, or more specifically, the horror stories associated with centrifugation going wrong, as is the case with the famous Cornell's centrifugation accident. There's a link to more about that accident in the published version of this article. Check out the episode description for all the details. Most centrifugation-related blunders are due to bad handling by the user. Therefore, it is crucial to understand why we do what we are doing during centrifugation, to avoid damaging the machine and personnel. Here are some of the most common issues that can easily be overlooked during centrifugation. First, it's all about balance. Centrifugation produces centrifugal forces to effectively separate sample components based on size and density. Small weight imbalances can cause abnormal vibrations that can damage the rotor. An unbalanced centrifuge is as dangerous as an unstable chemical reaction. It can not only damage the instrument, but can also start a domino effect of catastrophes all the way from instrument failure to sample breakage that could release potentially harmful contaminants into the environment, such as infectious samples and harmful aerosols, and user injury, overall resulting in large-scale destruction and posing a major safety hazard. Precise balancing is crucial during high-speed centrifugations. To understand this better, we need to go back to some basic physics concepts. According to Newton's second law, force is equal to mass times acceleration. Thus, the centrifugal force generated during centrifugation is directly proportional to the sample mass and acceleration. During circular motion, acceleration is related to the speed of rotation and the radius of the rotor. At high speeds, even slight variations in the sample mass can lead to substantial force imbalance, which could be catastrophic. Irrespective of whether the centrifuge has a fixed angle or swing bucket rotor, two important factors to consider when balancing include sample volume and the symmetrical arrangement of the tubes. It is important to ensure that the sample volumes are equal in all tubes and that the tubes are placed directly opposite each other in the centrifuge. If there is an uneven number of tubes, even it out by adding an extra tube filled with water to the same volume as the experimental tubes. If the solutions are not of similar density, example acetone and water, the tube should be of equal mass rather than volume to be correctly balanced. An additional factor to consider in the case of swing bucket rotors is to make sure that all the slots contain rotor buckets appropriate to the machine and of the same weight. Second, what about the difference between RCF and RPM and why this matters? RCF, or relative centrifugal force or G-force, and RPM, revolutions per minute, are commonly used to describe centrifugal speed. However, these units are completely different, and there's a link to an article outlining the key difference between RCF and RPM in the published version of the article. RPM denotes rotation speed, which depends on rotor radius. RCF denotes centrifugal force on the samples and takes into account both rotor radius and the speed of rotation. The same RCF can be achieved in centrifuges with different rotor sizes by appropriately adjusting the RPM. This makes RCF the go-to unit to describe centrifugal speeds, as it can be compared across centrifuges, whereas RPM is only constant for centrifuges of the same rotor radius. Simply put, RPM is not equal to RCF, and RPM speed settings need to be converted to RCF to ensure the correct centrifugal force is applied. Third is time, speed, and centrifugation. The choice of centrifugation speed depends on the size and fragility of the particles in the sample. The smaller the particle size, the higher the centrifugation speed. For example, bacteria cells are pelleted at higher speeds of 2,000 to 10,000 times G than mammalian cells at 500 to 2,000 times G. Furthermore, lower centrifugation speeds may be used with more fragile samples. Another critical factor that influences the efficiency of separation is RCF. RCF is proportional to the radius of the rotor and to the square of RPM. Due to the square dependence of RCF and RPM, Centrifugation speeds of 1000 rpm for 5 minutes and 500 rpm for 10 minutes are not interchangeable. The former produces a much larger RCF than the latter. Thus, it is important to consider RCF when determining the speed and time of your centrifugation. The fourth issue to mention is centrifugation at different temperatures. Centrifugation generates heat, which can increase the temperature within the centrifuge, sometimes by more than 15 degrees C, and there's a link to more about that in the published article. This can affect the stability of temperature-sensitive samples. In such cases, refrigerated centrifuges are usually preferred. However, constant temperatures can also be maintained in an ambient centrifuge. The sample temperature during centrifugation is primarily influenced by three factors: rotor material, rotor shape, and the speed of rotation. During centrifugation, the temperature can be influenced by the rotor material's thermal conductivity. Rotors made of metals such as steel and aluminium have a higher density and high thermal conductivity. They transfer heat efficiently and get chilled quickly. On the contrary, materials like polymers and carbon fibers are heat insulators and maintain a constant temperature. The shape of the rotor determines the airflow within the centrifuge, similar to how the blades of an electric fan influence airflow in and out of the machine. Optimizing the airflow within a centrifuge through rotor shape is essential to maintaining the temperature. The speed of rotation is directly proportional to the rise in temperature. At higher speeds, more heat is generated. It is important to understand the maximum speed of centrifuge and the range of speeds that maintain the temperature range that will not change the outcome of the experiment. Usually, this information will be provided by the manufacturer in the equipment manual to help the user understand the limitations and work around it. The fifth issue is to break or not to break. During centrifugation, the separation of the sample components continues during the deceleration phase. Many centrifuges offer the option to control deceleration settings, the brakes, to bring it to a stop faster. But when we do really need this option, what is the effect on sample outcomes? Braking can be particularly useful during centrifugations involving nucleic acid extractions or bacterial cell pelleting, which are not affected by sudden stopping. However, for experiments that are more sensitive to abrupt deceleration, such as isolation of peripheral blood mononuclear cells and gradient centrifugations, braking can cause separated layers to remix. In such cases, it is more suitable to turn off the brake so that the deceleration is gradual and does not disturb the gradients. Some centrifuges provide a range of deceleration settings. This can be useful when spinning mammalian cells, which are sensitive to sudden decelerations, but at the same time require some deceleration to minimize the time taken by the centrifuge to come to a stop. And finally, the sixth issue: where is the pellet? One of the most common applications of centrifugation is to pellet samples such as bacterial cells, mammalian cells, or nucleic acids. While using a fixed angle rotor, the angle of the rotor determines the position of the pellet. To ensure you always know where the pellet is, a good lab practice is to always spin the tubes with the lid hinges placed in the same orientation, for example, lid hinges facing outwards. This is especially useful to prevent sample loss during DNA extractions when the pellet is nearly invisible following ethanol wash step. In the case of swing bucket rotors, the pellets are mostly formed at the bottom of the tube. We hope this episode helps you to work more comfortably and confidently with centrifuges. If you have seen or lived through a centrifuge disaster, go ahead and share your story along with any tips and tricks to ensure happy spinning in the comments section of the published version of this article. May the force be with you. So that's it for the whats and whys of centrifugation. Check out the episode description for links to related articles and resources, and don't forget to subscribe to the podcast to get more help and advice from mentors at your benchside.